Hello, everyone, and welcome to AISC's Night School Fundamentals of Stability for Steel Design. This is presented by members of the Structural Stability Research Council, and today is Session 1, Course Introduction and Behavior of Compression Members. My name is Patrick Newman, and I'm with the AISC Continuing Education Group, and I'll be moderating today's presentation. I would like to introduce today's speaker. Ron Zimian is a professor of civil and environmental engineering at Bucknell University. In addition to authoring papers on the design and analysis of steel and aluminum structures, Ron is co-author of the textbook Matrix Structural Analysis and the editor of the 6th edition of the Guide to Stability Design Criteria for Metal Structures. He is currently chair of the Structural Stability Research Council, as well as AISC's Task Committee 10 on Frame Stability. He recently completed his term as chair of AISC's Task Group on Inelastic Analysis and Design. He serves on the AISC and the Aluminum Association Specification Committees and is active with the Steel Joist Institute. In 1994, Ron was awarded the ASCE Norman Medal, and in 2006, he received AISC's Special Achievement Award. Last month, Ron received the ASCE Short Ridge Hardesty Award for his substantial accomplishments in research, service, and teaching, as well as advancing practice in the field of structural stability. And with that, I'd like to turn it over to you, Ron.
Well, thank you very much, Patrick. It's my pleasure to be participating this evening. Just change slides here. First, I should mention that the Structural Stability Research Council is very pleased to be joining AISC in delivering one of their night school courses. As the title of the course indicates, over the next several weeks we will be focusing on the basics, the fundamentals. So really nothing super sophisticated, but simply those topics that one might consider essential to the stability of steel structures. A little bit about the course. The session topics include 2 lectures on compression members, 2 on flexural members, 2 on systems and beam columns, and then the last 2 will be on bracing. Each one of these session topics is presented in 2 parts. The first part, for example, tonight's lecture, will focus on the behavior in the background, and then the following lecture on that topic will focus on the design issues. So our lectures are all being given by members of the Structural Stability Research Council, and they include Perry Green, Todd Helwig, Don White, Joe Yura, and myself. And again, it's great to be joining AISC with this effort. As I said, the focus of the course is on fundamentals, and I think the first thing we should do, or I'd like to do, is just provide some working definitions. So I've got 3 terms here that I think are important and that really need to get us up and running. You'll notice that I'm not even going to try to attempt to define the word buckling. That has so many different definitions, and it's just been used so broadly that I think we'll just focus on 2 other concepts here. But first, in general stability, what that basically would mean to me, and hopefully to you, is that if a system or a component is under load and you were to provide some type of a small disturbance to it, upon removing that disturbance, the structure would return to the state it was before, still under that load. So it wouldn't fall over, tip over, or collapse or anything like that. So that's in general stability. Now when we go into the worlds of buckling, there's basically 2. The first we might call bifurcation, or critical load. This is more of a theoretical thing. It's really a theoretical point in which loading a component results in an instantaneous change from its current state to a significant amount of deflection. So those are big words. What's that all mean? The bifurcation is simply a theoretical point where you go from it's not buckled to it is buckled. All right? Instability, on the other hand, this is a much more realistic transition in which as you're loading a component, you're getting small deflections at first, and then all of a sudden you start getting some pretty significant deflections. and then finally you're sort of declaring the structure as unstable. So this would be sort of buckling preceded by significant amount of deflection. So tonight we're going to be looking at different possibilities here. We'll be in the bifurcation world for a while, and then we'll be spending a lot of time in the instability world. Some background on structural steel and how we get to all these stability issues. The first thing is that structural steel really has excellent strength-to-weight ratio and an excellent stiffness-to-weight ratio. And because of these awesome factors about structural steel, you end up using a lot less when you start thinking of economy and amount of construction materials. And as a result of being able to use less, your components end up to be very slender or skinny. Now, this inherent slenderness results in almost all strength limit states needing to consider some form of an instability. So like we said, we're going to look at course lectures, trying to understand the behavior, compression members, flexural systems, and then we'll finally wrap up with looking at bracing in order to increase the capacity of these members. So let's move into, so that was just a brief introduction of where this course is going and a couple of definitions. Tonight I'm going to focus on the behavior of compression members. Limit states of compression members. So we've got a bunch of different ones. The first one we could call full yielding. So we'll touch on that basically. And then instability. So it could be along the member length, and it could come in the form of flexural buckling, torsional buckling, or flexural torsional buckling. Or it could be at the cross-section in the form of local buckling. And so tonight we're really going to look and focus on this flexural buckling aspect. But before going there, let's have a look at the full yielding. So let's go all the way back to the beginning when we, were performing tensile tests, or if we took a piece of structural steel, put it in a testing machine and stretched it, and we monitored its stress and strain properties. And what we would see is basically on the screen here. We'd start off with no load, and as we applied load, we'd get a nice linear response. And at some point, I'm going to track the blue curve here, we'd get some yielding. We'd have a yield plateau, then some strain hardening. Eventually, we'd reach the ultimate, and then we would rupture the material. Now, this diagram is not to scale at all. Steel has some amazing ductile properties. And in fact, I tell my students that if they were to put their nose on the 0-yard line and reach out 1 yard to their right, this would be this point. And then if you were to look down at the 10-yard line of the end zone that you're at, that would be that point. And then if you could see the far end zone, that would be that point. So there's a lot of ductility going on with structural steel. Now, what we're going to do is assume that the material is elastic and perfectly plastic. So it either has its full modulus elasticity or the E value is 0. So we're going to be neglecting then the strain hardening. One of the things that we'll be doing this evening, because everything is in compression, is we'll be assuming that the yield strength for compression is the same as the yield strength for tension. And both of these then will be the yield value. And like I said, we'll also be neglecting the strain hardening, so we'll be assuming elastic, perfectly plastic material. So if we just think about the full yielding aspect, we could come up with our first column curve. And so over on the right here, I have a column we're testing. And what I'd like to do is plot the strength of the column versus its length. So on the horizontal axis, I have its length. And on the vertical axis, I have its strength. And if all we were to consider was yielding, what we would have here is a column that would always be able to reach its full yield capacity. So the question is this zone then in which you might be in, is it acceptable? And I think you're aware that for probably very short, stocky columns, we could reach the full yield. But the second the column has any significant amount of length, there exists the possibility of buckling, so some type of an instability. So I would say that this criteria, this column curve, would be unacceptable. And so what are the possibilities then? Well, we could have a member type of instability or a cross-section instability such as local buckling. And like I said, we're going to focus on the member instability part. So what are the possibilities of a member instability? Well, we could have flexural buckling like I'm showing on the right here. So here's a large test going on, I believe, at Bechtel. At Bethlehem Steel, an older photograph. And it actually may be a test being taken place at Lehigh now that I look at it more closely. But nevertheless, we've got a column in a giant machine being squished, and you can see that the column is flexing or bending and as it's reaching its buckling capacity. On the other hand, if you were to take a cruciform section and subject it to axial force, the failure mode would be very different, no flexing or bending, but much more one of twisting. So that would qualify as torsional buckling. Now, if you move away from a shape like I'm showing down here at the bottom, these bisymmetrical shapes, I shapes or HSS shapes or back-to-back channels, in which the centroid is in the same spot as the shear center. And again, the shear center is the spot that if this was a beam and you were to load it, it's the point where you could load without any twist occurring in the beam. The beam would just bend. So for cases like I'm showing over on the right here, a T-section or this channel, where the centroid and the shear center are not at the same location. So for the channel, for example, the centroid it's where the x and y axes intersect, and the shear center would be out here someplace. If you subject these to compression, you're not going to get just flexural buckling. You'll get twisting as well. So we tend to call this flexural torsional buckling. So those are the ones, and like I said, tonight we're going to focus on this flexural buckling case. So flexural buckling. Well, what we're going to do is we're going to start having a strong look at Euler's column, his solution, and the assumptions he made. And then we're going to try to approach reality by undoing each one of those assumptions and what's involved with undoing the assumptions. And then I'll end up looking at column curves, one, what's in the AISC specification, and then what some others are doing elsewhere in the world. So Euler buckling. All right. I'm going to get my notes together here. Euler was a Swiss mathematician and physicist, and 270 years ago, he was out solving some math problems and stumbled across a structures problem in which he solved using differential equations. So this was in 1744. Over on the right was the publication in which this concept first appeared in. 1757, that's 13 years later, and that's when the AISC specification adopted Euler buckling. Okay. All right, that was a joke, but because we're on a webinar, I can't hear all the laughter. Obviously, there was no AISC. There was no A, as in America at the time, either. So this was a long time ago. But anyway, Euler buckling. Some assumptions. Euler assumed that the member was prismatic, so it had a constant I along its length. We had small deflections just at buckling. We had no bending prior to bifurcation, so Euler is going to talk about buckling. So the column, as I'm showing down on the right here, is either perfectly straight with load on it, or 1 instant later, it's buckled into this flexural shape that I'm showing on the right. So no bending, which means it has to be perfectly straight, and that load has to be right through its centroid. We're going to assume, Euler is going to assume linear elastic behavior, so the E will be constant, and the support conditions are going to be pinned roller. So what is Euler going to do here? Well, what we basically do is we start just after the column buckles, and only a small amount of buckling, small amount of deformation, but we have reached the Euler buckling load. So what I'd like to do is draw a free body diagram. So I'm going to make a cut here, and here is the upper portion of that structural member. We've got the axial force, the Euler buckling load on it. The member is flexing, and the deflected shape is being described by this function v of x. And to have equilibrium down at the bottom here at my cut, which is x away, we have an axial force acting upward and a moment in the column. So we've got two things we can work off of. First, just equilibrium. If we sum moments about the base here, so here's the base, it's star, and I sum the moments, well, what have I got here? I've got the moment, okay, m of x, and I also have this Euler force acting through a moment arm v of x, also contributing to that moment equation. So those are the two components of moment. I add them together, and if the thing is just in equilibrium, it should equal 0. Now this moment term here, m of x, is related to the deflected shape v of x, and that's our moment curvature relationship. So I'm sure all of you know this moment curvature relationship. You've been using it in moment area, conjugate beam, whatever method is your favorite method for calculating deflections, and it's basically that the internal moment in the beam is equal to EI of the beam times the second derivative of the function that describes the deflected shape. All right, so what we're going to do next then is we're going to make a substitution, and we're going to substitute this term in for m of x. So when I do that, down at the base here, over on the left, what I end up with is a differential equation. All right, so don't go running out of the room yet. Stay here. It's not over. You can solve a differential equation. No, you can't. All right, if you can't solve a differential equation, well, most of our students can either today, and what they've been all relying on is their new calculators, which have symbolic processors in them. And so it seems that they just smile when you tell them, all right, you got to solve the differential equations, where years ago we used to just cringe. But I do reference you to some fun software at this website here, where you can just type in the differential equation, hit go, and it will give you the solution. But anyway, we've got this second order differential equation, and voila, over on the right here, I've solved it. And what it's basically telling me is the function just at buckling, v of x, is equal to a constant times a cosine plus a constant times a sine. So in our quest to find out what those constants are, what we're going to do is have a look at the boundary conditions. So I had described this point as my origin. So at x equals 0, we should have no lateral displacement. So v at x equals 0 should be 0. So if I come up to this equation and I plug in 0, the sine of 0 is going to be 0. The cosine of 0 is going to be 1. So v at x equals 0 is c1, and c1 needs to equal 0 for that boundary condition to be satisfied. So what that basically means is that this term is not in the equation at all. It's also telling us that the buckled shape is a sine wave. All right. So let's use our second boundary condition then to see what information we can get from that. So we've got the fact that the curve is a sine wave, and in our quest to find out what C2 is, we say, all right, well, v at the far end at x equals L, the lateral displacement also has to be 0. So we got 0 is equal to C2 times the sine of that portion there. And again, we're computing this at x equals L. Now, we've got two solutions. The first is what the mathematicians call the trivial solution, and we could just call C2 0. The problem is if we call C2 0, then v of x is 0, which means basically the column never buckled. But we're looking for the buckling solution. So we're going to ignore that trivial solution, and we're going to go to the second possibility, and that's that this sine term right here, over this portion here, must equal 0. So if we take that and we realize that sine takes on a value 0 at n pi, where n is 1, 2, 3, or 4, 5, 6, 7, 8, whatever you've got. So we've got in this portion here, it needs to equal n pi, square root of p, or the Euler buckling load divided by EI times L must equal n pi. We can solve then for the Euler buckling load, and it's n squared pi squared EI over L squared, where n takes on the values 1, 2, 3, etc. Now, as I indicated earlier, Euler is solving for the bifurcation load. So what that means is if we take our column, so here's the column, and we're loading it up with our axial force, if we were to monitor the lateral displacement, we would have none, no lateral displacement, no lateral displacement, no lateral displacement, until suddenly we hit the Euler buckling load, and then we would have bifurcation and the deflection would become unbounded. So that's what we're saying. Now, the second thing is you can see that it's difficult, well, impossible, for us to get above the first buckling mode. Because if we want to get up to the second buckling mode, where n equals 2, for example, and the buckling load is 4 pi squared E over L squared, again, that n is squared, as you can see in the upper right, that's 4 times as much load. Well, to get to, let's say, 4,000 kips, I would have to go through 1,000 kips first. And when I went through 1,000 kips, the column would buckle. And likewise, theoretically, we could find the third buckling mode, n equals 3, n squared is 9, and we could have 9 pi squared EI over L squared. But the bottom line here is that the first mode is going to control. But you might ask, well, is there any interest in these higher modes? And the truth is, yeah. If we start thinking about where to brace the column, these higher modes might tell us, this, for example, might be a good point to brace it. So if we start thinking about optimal location of bracing, and those higher modes could be very useful. So, okay, so we've made a big step here. We've now got the Euler buckling stress. And how we get that is we take the Euler buckling load, pi squared EI over L squared. So this capital E down here, that's capital E for Euler. So the Euler buckling load is pi squared EI over L squared. And if we divide by the cross-sectional area of the column, and we introduce the radius of gyration as the square root of the moment of inertia divided by the area, we end up with an expression that says that the Euler buckling stress for the member is pi squared E divided by L over R quantity squared. So we've now been able to take into effect the fact that the member may buckle. So we've got a second chance now at a column curve. We'll take the information we knew before, and that was we could never get above the full yield, sigma y. But also on this now we can include the Euler buckling stress. And you can see what happens here is the column gets long and slender. So now I'm plotting L over R, the slenderness on the horizontal axis. As it gets longer, the Euler buckling stress gets much, much smaller. So it's easy to buckle a column that's long and slender. Now, an interesting thing happens is when the column, say, gets below in this slenderness range, we might try to get to the Euler buckling load, but we can't get to it until we fully yield the column. So we've got now our second take at a column curve that says anything that's in this green area here below full yield and below the Euler buckling stress should be acceptable. And life would be great except for Euler had made several assumptions. So we need to go back and have a look at those assumptions.
Ron, can I interrupt for
sure.
a second here?
Yeah.
I got a question, and it's going back on slide 13. What are you talking about? I'm switching to slide 13.
Yep.
And the question is, in what type of sections does torsional buckling control over flexural buckling? Even if the centroid equals the shear center, like in the cross-section, torsional buckling is possible. And if you could clarify that for us.
All right, that's a really complicated question. I would say it's 99.9% of the time in a section that looks like these over here, you're never going to have torsional buckling controlling. So the only situation where this really starts to develop is for the cruciform section. So if you don't have a cruciform section and your centroid and your shear center is at the same spot, then the flexural buckling should control. Now you may have some very strange boundary conditions, but I'd have to think these are very theoretical, in which you've prevented the flexural buckling from controlling, and you have made the column so long that the torsional buckling solution could creep in there. But I think that would have to be a very, very long member, or a very strange set of boundary conditions that prevented the twist over did not prevent the twist over a very long length. So I think that's about the best I can do with a quick answer.
Okay. Okay, thank you. So we'll go back to where we were. Thank you, Ron.
All right, great. So on the assumption side then, so Euler, like I said, had assumed the members were prismatic. Now we do have non-prismatic members, and that's a great topic, but we're not going to go there tonight. So let's assume that we're looking at standard wide flange shapes or HSS shapes where the member is prismatic over its whole length, a constant I. So we're going to move to the second one, and that is small deflections after buckling. So that's not so bad, but it's this one here that is really going to cause us some trouble, in that there's no bending prior to bifurcation. So this bending can come to us in two ways. One, prior to the bifurcation, or the column just simply is not perfectly straight. So if the column, as I'm showing down at the bottom here, is not straight right from it being shipped from the mill and into place, then as we load this thing up, it's going to produce, there's going to be a small amount of bending, and it's going to produce more bending. And so that would be the first case. And the second case, which is just as likely, but one we won't look at tonight, and that is that the axial load is not concentrically applied. You know, it's small. You almost got through the centroid, but I think it would be unrealistic for us to assume that we could ever get perfectly through the centroid. So we do have some small eccentricity, and as a result of that, we would be picking up some bending. Okay, so now we've got bending. So let's see if we can track a solution and see what happens with bending. So to do this, what I'm going to do is I'm going to go back to the Euler column, and I'm going to put in, I'm going to just put in a small amount of out of straightness. And to keep things nice and clean mathematically, my out of straightness is going to be defined by a sine curve. And I picked a sine curve because you know that's what Euler's solution was. So I'm going to have a sine curve that comes along here, and it's just a small amount. And let's say at L over 2, where the sine of pi over L times L over 2 would be 1, I'd have some type of a magnitude of an initial imperfection, say at midspan of L over 1,000. So I'm talking about a very small amount of initial out of straightness being described by what I call V sub 0, or V original function. Same things as before. Now we've got that initial imperfection, V0. We start applying the axial force, and as we apply the axial force now, the member which started at the blue dash curve is going to start bending, and it's going to start moving over to the right. So what we're going to do is we're going to pick up deflection due to the axial force. So that's what I'm going to describe as V sub P of x. So the total deflection from it being perfectly straight all the way over then is the sum of the initial imperfection plus the bending deflection that's being caused by the axial force. Now what we can do then is keep working. We'll set up equilibrium. So I'll pick some point like I did before in the Euler buckling problem, say this point here. And I'll solve for equilibrium, and I have the moment down at that point, the internal moment, and that's being produced by that axial force P, plus the axial force times the moment arm, and the moment arm again goes all the way from where the axial force would act all the way out to where the member is bent to. So that's V of x. A substitution using our moment curvature relationship. So that moment is equal to EI times the second derivative, now not of V, but just of the function Vp of x, the deflection being caused by the axial force. So we have the second derivative. So that's our moment curvature relationship, the axial force, and then the total deflection is the original deflection, the initial out of straightness, plus the deflection being caused by the axial force in causing that amount of bending. So just work down one more. I did a little bit of algebra. I got all the VPs on the left side of the equation, and on the right side of the equation I have V naught. And then the last thing I did is I just substituted in for V naught that expression delta naught. So that was the math equation that I used. So now I've got one more differential equation. And so here is that differential equation coming to you from the previous slide. And again, I didn't run out of the room. I relaxed, and if I was petrified of trying to solve it by hand, I could go to some software or a website, plug in my differential equation, and what would pop out here is the solution for Vp of x. So this is a function now that's describing how much the deflection, the lateral deflection, moved over from its initial out of straightness. And I agree, it's kind of a scary looking equation. It is a sine curve, remains a sine curve. But down in the base, there's a very interesting result that occurs when you actually factor in the boundary conditions. So I've shown the two boundary conditions here. X equals 0, Vp is 0, x equals L, Vp is 0. And when you plug those two boundary conditions in and solve this thing, you end up with this expression with EI pi squared over L squared. Now we've seen that before. In fact, that's the Euler solution. So if we substitute in P Euler there, we end up with Vp of x being this expression over here. So I agree, things are getting a little mathematical. But hang with me, that's not a complete nightmare. It's just some algebra. Moving along now, what we're going to do is make two substitutions. So here's what I'm after is the total function v of x. So the first one is v of x was supposed to equal the original initial out of straightness plus the bending deflection due to the axial force. So the original one was delta naught sine. Vp was what we just solved in the previous slide. I'm going to substitute both of those in and get myself an expression for v of x, which is down at the base here. And again, here's an equal sign. I'm just going to do a little collecting of terms, and I end up with this expression here. So this is starting to look more interesting, but just trying to show you the in-between math. So let's take that one step further. So here I was with this expression here, v of x. That's coming from the previous slide. And if I actually work with this term that's in the parentheses a little bit, what I get back is a more simplified version, and that's this term here. And this term here is very interesting. So what we've got now is we have an expression for the lateral deflection v of x, and it's equal to this amplification factor, if you will, 1 over 1 minus p over p Euler times the original deflection function. So this is very interesting. So now what we can do is we can go back. We have the deflection curve. Is we can start applying the axial force, and we can start plotting and seeing what that deflected shape what the response curve looks like. So I guess what I'm going to do, one thing first is let's take it at a specific point. So instead of just having v of x in general, let's focus on mid-span, so at L over 2. So at x equals L over 2, we're going to monitor the deflection at that point due to the axial force. It's the amplification factor is the same, and v naught at x is just L over 1,000 or whatever it is, delta naught. So this is the one actually that I'll plot up for you more specifically. So here we go. So here's what I've got for you. On the horizontal axis, I'm plotting the lateral displacement at mid-span. On the vertical axis, I'm plotting the axial force. And in the red curve here, what I'm monitoring is the lateral deflection. That is the deflection from this point over to this point. And you can see when there's no load on the column, I would just have delta naught. And then as I put more and more axial force, really nothing happening. And then all of a sudden, my deflections, the lateral deflections, again, deflections this way, are going to start growing, and then all of a sudden I'm going to hit a point where they're going to start getting fairly big. And what's really interesting is that as I put more and more load, the lateral deflections start to become unbounded as I approach the Euler buckling load. So what's happening here is, I'm trying to say in words, is an elastic instability occurs as the compressive force P approaches the Euler critical load. So we've used two different approaches to sort of get the quote-unquote buckling capacity. Earlier we used a bifurcation analysis, and now we've used an instability analysis, and both of them are ending up at the same point. Now you might not be too happy if you let your column curve or column strength be controlled by the Euler buckling load, because like I said, for real columns that have some type of an initial out of straightness, the lateral displacements are going to get fairly large before you even get close to, or as you get close to that Euler buckling load. So what you might have a tendency to do is say, look, that's as much lateral deflection as I want, and then you can scale back and find out, that's it. I'll just put on, say, 85 or 87% of the Euler buckling load, and I can live with those deflections. As long as I'm below that, I'll be fine. So what we can be doing here is to prevent excessive lateral deflections, we can limit P to some proportion of PE. And so I have called that alpha PE. And later, when we take a look at the AISC column curve, we'll find out that that value is actually 0.866. But we're getting ahead of ourselves. So here we go. We're ready then for take 3 on a column curve. All right? And all the differences now as far as the bending goes is we're just going to make sure we don't, as we get close to the Euler buckling load, we don't let the lateral deflections get too large. So column curve 3 looks very similar to column curve 2, It's just that I've taken the Euler buckling stress and I've reduced it by some factor alpha to make sure that the lateral deflections don't get too large. Is it acceptable? Well, unfortunately not, because we have yet to consider yielding due to bending plus axial force. So we've got to think about this inelastic problem. So that is where Euler got us into a little bit more trouble. We've undone the bending, but unfortunately when we did the bending, we introduced the possibility for some yielding, and Euler had assumed everything was nice and happy and linear elastic. So let's try undoing the assumption of the linear elastic behavior. So I need to review some basic pure bending in a beam. First, I'll take an easier case, and that's just major axis bending. So I'm going to apply a moment at the end of some small segment of beam, and I'm going to monitor the relative deflection between the two ends. All right, so that's what theta is, and on the vertical axis, I'm plotting the applied moment. And at first, I'm just going to have a nice, happy, linear response. We've got a EI elastic. And we've got MC over I as our moment diagram, and we couldn't be more pleased. But eventually, as you're aware, we're going to reach some point at which just at the top and just at the bottom of the flanges, we're going to get some yielding. So we've described that as the yield moment as the product of the elastic section modulus in the yield strength of the material. So at this point right here, we start to get some yielding, and get more yielding through the cross-section. So you can see the yield zone coming from the top and from the bottom and coming towards the centroid. And eventually it gets pretty damaging and takes out the whole section, and we eventually form what's called a plastic hinge, and that's at the plastic moment capacity, which is equal to the plastic section modulus times the yield stress of the material. Now, an important thing to note is that everything was happy as long as we had no yielding. We had the full EI. But the second the section started to yield, we started to lose E. In the yielded zones, we assumed the material was elastic, perfectly plastic. So once it's yielded or perfectly plastic, it has no E value. So the only section remaining with E, modulus of stiffness, is in the red here. So the EI for this partially yielded section is less than the EI for the elastic. And as the section gets more and more yielding, the EI becomes significantly less. All right, so that's for major axis. And I have to say that in major axis bending, this ratio is usually, if this was 1, this might be 1.15 or something like that. It's at worst case scenario about 5/6 of the way up there. But things get a little bit more interesting when you take a look at minor axis bending. So still reviewing the behavior of a beam subject to minor axis bending. So I've now rotated the beam 90 degrees, and I'm now subjecting it to a minor axis moment, again monitoring the relative rotation. Everything is nice and happy and linear elastic up to this point, in which at this point here we just yield the flange tips. Once we yield the flange tips, again, the slope of this curve is its stiffness, or its EI. We start losing stiffness, we start losing EI due to yielding, and eventually we'll find ourselves a plastic hinge just like we did for major axis bending. Now the difference here, though, in minor axis bending is much more significant. The second you start losing those flanges, you really start hurting. And so this is, the difference here is about 2/3, where before it was about 5/6 or even better than that. So something to think about. If this was 1, this would be 1.5. So there's a lot of zone now in which you can undergo a significant amount of partial yielding where you've lost a lot of stiffness. Now, that's just pure bending. Let's introduce some axial force. And so over on the right here now I've got bending plus axial force on my section. Everything is nice and happy. MC over I is no longer the case. I now need to do MC over I plus P over A. So my stress diagram is still linear, but it's no longer going through the centroid. I load to about this point here, and suddenly P over A plus M over S out in those flange tips reaches yield. And at that point, the section starts yielding. So probably in this case, because of the way we're loading it, the top flange tips would yield first, they'd start yielding. Eventually those bottom flanges would yield, and the whole time again we're losing bending stiffness. So just a small amount of axial force starts to reduce when the initial yield starts. And also notice that we can no longer get to the full plastic moment capacity anymore. We get to a significantly smaller amount. Now, we don't have small axial bending in columns. We have large axial bending. So I just wanted to walk you through. This would be the same curve if we had just moderate axial bending. You can see a significant shift now. We're getting yielding early on, and we can't even get to the plastic moment capacity. The plastic capacity can't even get to the yield moment where there is no axial force. And then if we really get to what a column is, the picture looks something like this. All right, so here we are. We're loading up with a large amount of axial force, a small amount of bending. It doesn't take much before suddenly we yield the section. P over A is a large number, so M over S just needs to be a small number. We yield. We probably would, again, we would yield the top flanges in this case. And from this point through, what basically happens is it comes down very quickly just as a result of that small amount of bending. And again, we lose the stiffness. So there's a takeaway here that I'm looking for you, and that's that just a small amount of bending can quickly lead to a significant amount of yielding and a heavily loaded compression member. So this bending, even say, oh, it's just a small amount of bending, it shouldn't matter. It actually has a big impact because it causes yielding, especially in the minor axis. Now I want to return to another picture that I was showing you earlier. And this was, we were back looking at this, and there's a golden opportunity just to have a discussion here to plant a seed for a few weeks from now. We had been looking at the bending of this column, and it started with an initial imperfection, and this was that term there. And then we started applying the axial force, and we started getting some bending moment to develop. And we had actually used differential equations, and we developed this expression together. Now what I want to do is we start with equilibrium. Okay, so we've got our equilibrium expression. But I'm not going to do a moment curvature substitution or anything like that, get anything scary. I just want to do a little bit of math with you and show you that if I take and bring the PV term over to the right-hand side, I have minus PV. So now I have an expression for the moment. And what I'm going to do for this term right here, the V of x, is I'll substitute in our solution from earlier. And that's what's sitting here. Then I'll collect some terms together. And all of a sudden, once again, this amplification factor that we've seen earlier now is popping out again. And we've got this expression here. Now this expression here is very interesting. This is just what we would call the first order moment. So if we were to actually do equilibrium on the undeformed shape, so the undeformed shape would include the initial imperfection, but that would be it. This would be the moment that we would have. But as a result of the member flexing and bending, we pick up second order effects, and the actual moment that's in that column is really the first order moment, which would be equilibrium on the undeflected shape multiplied by this amplification factor. So a lot of you have seen this B1 factor that appears again and again. Here's a place where it's coming in for us, and we just had a convenient point to talk about it. Now, you can actually take advantage of that. Like I said, life is good. Here's the equation for that bending moment. Let's say, where is it going to be a max? Well, at the midspan. So I plug in L over 2 for x, and the axial force is P, and I have this expression. So all I've done is plug in L over 2 into this point right here. And now I have the bending moment, say, at midspan, where I know the moment is the largest. So like I said, all is good as long as all is elastic and no yielding. So this would be your P over A, and these are just absolute value signs, so I don't get triggered by the signs, plus M over S. But once yielding occurs, these two would equal, the sum would equal the yield stress. And so what you can do is you could actually make a substitution for M. I've got this expression here. So I plug in for that, and now I've got a single expression that has the axial force P in it. And everything else I know. I know the Euler buckling load. I know the initial imperfection. Let's say it was L over 1,000. I know the cross-sectional area, the elastic section modulus, the yield strength. So this is kind of a fun little equation that allows me to calculate for a column with an imperfection when yielding would first occur. Anyway, let's keep moving along. And like I said, once this yielding occurs, things really hurt. And so what I'm showing you here is we're loading up the column. We're getting quite a bit of bending. We start to get some yielding. Once we get yielding, from those earlier slides I showed you that we'll lose stiffness, EI. Once we lose stiffness, our bending deflections increase. Once our bending deflections increase, they're being multiplied by P, our internal moment increases. Our internal moment increases, which produces more yielding, and we get stuck in this little cycle here until hopefully the system reaches equilibrium. Then we apply a little bit more load. We apply a little bit more load. The yielded portion loses stiffness, increases deflection, moment increases, more yielding, and we go through this little cycle until the system equilibrium. So we keep repeating these steps until finally we apply enough load that we reach an instability that includes yielding. So what I wanted to do is just show you these results now. So that's what we're going to see here. So this curve should look familiar to a curve I showed you earlier. I showed you the curve that looked for a column that has a small initial imperfection. We applied the axial force, and we monitored the lateral displacement delta, in this case at mid-span. So we had a small amount of an initial imperfection with no axial force, and we start putting on the axial force. And earlier, we tracked this blue curve, which is nice and happy, and went right up and approached the Euler buckling load. But once initial yielding starts, life is quite different, because once initial yielding starts, we start losing the EI. And once we start losing the EI, we unfortunately cannot asymptotically now approach the Euler buckling load, but some inelastic buckling load that I show in the red curve here. So we've got the strength of the column and inelastic instability occurring, and it could be occurring well below that of the Euler critical load. Another interesting thing is that the smaller the column slenderness, so the smaller the L over R, the difference between P sub n, the inelastic buckling load, and the Euler buckling load. So keep in mind, when L over R was small, the Euler buckling load was very large, and we could never get there before we would yield the column and get this inelastic response. So now we're starting to approach an inelastic instability, and unfortunately, it does not approach the Euler buckling load. Now you might be wondering, all right, that's all well and good, but where is P sub y? And P sub y, again, is just the squash load of the column, the area times the yield force in the column. And we've basically got two options where P sub y could be. The first is it could be in between the Euler buckling load and the nominal strength. All right, so this might be in a moderate slenderness column. Or if the column was very long and slender, the Euler buckling load would be below P sub y. All right, so P sub y could be of one and two spots. The one place it cannot be, though, is below the inelastic buckling load. All right, so you can't get, you would have inelastic buckling before you would reach P sub y. And then, like we said here, the larger the column slenderness, the more bending, and the further Pn is below Py. All right, so again, we're trying to put things in perspective as where are these values occurring. So with this knowledge now of bending and yielding, we can start to put together an inelastic buckling curve. So that's what I'm showing here. So we've got axial force, lots of it, plus a small amount of bending could cause yielding. As L over R is small, now we'll call our critical load as sigma y. So L over R small on our column curve. So here's the fourth take at our column curve. It's small, and we're going to be close to the full yield. As L over R gets large, so we get out in this zone, we're going to certainly, the buckling stress will be below sigma y. And as it gets really large, it will asymptotically approach the Euler buckling force. So that essentially what's happening when you get all the way out here is the column is so slender that even though you do get some bending, you don't get any yielding before you get the Euler buckling load. Now before, though, we did say we also wanted to limit the deflection, so we took the Euler curve and we brought it inward. So now we've got this inelastic curve, column curve, and it transitions into a reduced Euler curve. All right. So is this acceptable? Well, we're almost there. The only problem is that our steel sections have residual stresses. So I'm going to give you a quick review of residual stresses. So residual stresses are sort of these built-in stresses. They usually come from an uneven cooling, or after you either weld something or you manufacture a shape, you can get residual stresses upon cold bending. The magnitude and distribution of the residual stresses in the cross-section are a function of the cross-section and its dimensions, so it's not like one size fits all. The residual stresses are usually, if not always, independent of the yield strength, even though we often say, oh, they're 20% or 5% or 13% or whatever. They are independent of steel yield strength. In the thermal residual stresses, basically what's happening is they occur in wide flange shapes because the locations with a high surface area, those flange tips, cool well before locations with smaller surface area. So I've got a picture here. I'm going to just take a sip of water. Right at the end of the rolling process. So these wide flange shapes have just finished rolling, and they're being put aside in a cooling area, and you can see they're red hot, and they're going to start cooling. And as you move across the picture here, you can start to see that the areas that have the most surface area are the ones that cool first. So let's walk you through that differential cooling process and what results. So originally, the entire section is hot, and it starts to cool, and when it does, as anything, when it cools, it contracts, and everything is happy and free to contract. The E value is very small, because the temperature is so high. But eventually, those flange tips, which I'm showing in blue over there, they cool, and when they cool, their E value starts to approach 29,000 or 80% of it or whatever, so they get very stiff, and they don't want to contract anymore. Unfortunately, at the web flange intersections, those red spots, they're going to cool later, and when they finally want to cool themselves, they want to contract. But the flange tips have already cooled. They've already set. They've got an E value. So the flange web intersection, it can't contract. It wants to, but it can't. So you end up with a result in which the locations to cool last, that flange web intersection, end up in tension. They want to cool. They want to contract. And the flange tips are preventing them. And by preventing them, they're ending up in compression. Now this picture is just a cartoon here, but over on the right is really a closer picture of what the actual distribution looks like. So out on the ends here, we end up with the flange tips in compression. At the intersection, everything's in tension, and depending on the shape of the cross-section, we can have this area in tension, and back in compression. And this is in tension, flange tips in compression. The whole residual stress pattern has to be in equilibrium, but it certainly varies across the cross-section. And again, the killer is that these flange tips are in compression. Now, if you actually go and have a look at real cross-sections, and people have measured these residual stress patterns, you can see that they vary. On this axis here down this row, we've got the flange pattern, and on this one, the webs. And depending on whether you're looking at a very light W shape or a really heavy W shape, you can get different variations. But in all cases, these flange tips are ending up in compression. The big difference is what's happening with the web. I've got two slides over here. It happens with roll shapes, and it happens even more with welded shapes. Now, some people have put some math to this, so often in computational studies or that work, we can assume different stress patterns. Over on the left is one assumed by Galambos and Ketter, and over on the right is one that the Europeans use. The thing to note, though, is the size of these residual stresses are on the order of 30% of the yield. In this case, of 50% of the yield. So for a very square sort of jumbo shape, we're talking about residual stresses on the order of 30 to 50% of the yield. And that's a lot of stress to have in your column before you even put any load in it. Now you might be wondering, how do they even compute these values? Well, there's two ways to get residual stresses. Let's start with the one on the right here. It's kind of a fun one. We take a specimen, a sample, and out of it we cut a test piece. So over here we've got the test piece. And what we do is we're going to actually cut this test piece up into a whole bunch of sections. But before we cut it up, it's hard to see in the picture though, but we're going to mark it with some gauge length. So here's a pinpoint, and at the far end is a pinpoint, and then the distance we'll record as the gauge length. Then we're going to cut this test piece up into a whole bunch of segments, and then we may even take those sections and slice them into smaller pieces. So you can see once I cut it up, I remarked it here with pinpoints along the depth, and measured those and cut it again. And by monitoring the total change in length that occurred, so here it was in its stress state, here it's in its unstressed state. When it's in its unstressed state, it's for example, those compression flanges were in compression. Once we release them, they're going to get longer. And so we have the change in length over the original length, which came from our gauge length up here. Hooke's law can give us the magnitude of the residual stresses, and that's how they can actually figure out what the distribution is. Now, another way to get some information about residual stresses is to perform a stub column test. So here we're going to take a column whose length is very short. It's usually about twice, maybe 3 times, but usually about twice the depth or width of the section. And apply an axial force, and we'll monitor the response. So I'm going to do that in this next slide. So an interesting thing happens now. So over on the right is what I'm going to do. I'm going to take this small stub column, I'm going to squish it, and I'm going to have these gauge lengths set up, L, and I'm going to monitor the change in length over L. And here's what the response would look like. So on the horizontal axis, I have the change in length, and on the vertical axis, I have the applied force. Now, what you would think would happen is we would just load this thing up, and it would take load. Again, we're measuring longitudinal deflection, not lateral deflection, but deflection in the direction of the load. And you think we'd just load this thing up until all of a sudden it reaches its squash load or full yield, and it would come across. But if you do these tests, and we've done them in the lab, and they're kind of fun, as you're loading, the response is linear, and then all of a sudden you hit a point in which you transition into a nonlinear response. And what's happening here is those flange tips, which were in compression now, they reach their yield. So we had the flange tips with some residual amount of stress, and then we add P over A, and we reach yield. So the flange tips yield, we lose axial stiffness. The second we lose axial stiffness, the slope declines, and we asymptotically then approach more yielding until we actually approach the yield load. So again, we're getting partial yielding in the cross-section as a result of the presence of the residual stresses. Now, once we see this break point in the lab, if we can declare it, we know it's whatever the residual stress is out at the flange tips or in the center of the web, plus the P over A that we're applying must be equaling sigma y. That's why the transition from linear to nonlinear, so then we can back calculate what the residual stress is. So 2 different ways to figure out those magnitudes, but this one also provides an interesting equation for you. And that is, some folks have gone back, and this dates all the way back to the CRC column curve days. What are we talking now? 40, 60, probably 60 to 70 years ago. And what you can actually do is we declare, all right, so the residual stresses, let's assume that they're 50% of yield. And what you can do is fit a curve then in which the EA effective is what you're monitoring. It's equal to some tangent modulus times the area. And that tangent modulus you can describe as tau times E. And so your tau factor, when everything is nice and linear, it should be just 1. So as long as we're less than 50% of yield, our stiffness reduction factor would be 1. But once we get above that, we can start reducing it with a rather simple looking equation that was actually, like I said, the basis for the AISC column curve for many years. Now I show you this as a little tidbit because later we're going to talk about the direct analysis method, and some of you may have looked at it before. This is where that tau factor is coming from. But again, we might be getting a little ahead of ourselves. So, like I said, that tangent modulus approach can provide us then the opportunity to modify our Euler buckling stress to account for yielding due to residual stresses. So column curve 5, take column curve, take 5. We've now got the Euler column curve being reduced for the residual stresses, the yielding, and we've got the green curve. And is this acceptable? Well, unfortunately not, because it doesn't include the initial imperfections, those bending effects. But this was, like I said, the column curve in AISC for many years. Now, what's interesting is these compression members. We need to have bending and residual stresses. That's what we're after. Bending without residual stresses, that's what the British standards did from like the 1950s to the 1970s. No bending, but with residual stresses is what AISC did. So what I'm saying here is that in the US, all of the columns were perfectly straight but had residual stresses. And in England, all of the columns were imperfect, and they had an out of straightness, but they had no residual stresses. So we had two very strange situations. It was the same column, but interpreted differently depending on which side of the Atlantic Ocean you were on. Now, let's get back to including that partial yielding. So we've got the residual stresses. We have the axial force stress. We've got the small amount of bending, and the total needs to equal the yield. All right, so what I'm trying to show you here is here's our I shape. Here's the residual stress pattern. Here's the addition to it. As we apply the axial force in the column, we also pick up a small amount of bending. So the total stress, the residual, plus the axial plus the bending gives us this profile here, and eventually, like I was saying, those flange tips yield. Once they yield, we start losing flexural stiffness, and we can get ourselves into a column buckling. So just to show that this is real, or at least real by finite element world, what I decided to do for you is show you the minor, so run some analysis for you. So I took a W14 by 145, A992 column, and for a whole range of L over R's from 0 to 200, I plotted one, here's the squash load, sigma y. All right, looks like I've normalized the axis. So sigma equaling sigma y is 1. I plotted Euler's curve for you, and then I plotted what the finite element results would give for a different L over R ratio. So let's take L over R, I don't know, about 60 here. So if you include only the imperfection but not residual stresses, you'd be at this point. Include the initial imperfection and the residual stresses, and you drop down to this point. So those residual stresses do have a significant impact on a column that has an imperfection. So we moved from here down to here due to the imperfection, and then down to here due to the residual stress. Now things aren't quite as dramatic for major axis bending. You can see that curves are a little bit tighter, but still the impact of residual stresses is notable. Just to take it a little bit further, what's happening in this curve is I'm trying to show you a comparison of the major axis column curve versus the minor axis column curve. And what you can see here is that minor axis column curve has less strength than the major axis one for a W14 by 145. All right? And again, my initial imperfection was a sine wave with a maximum amplitude of L over 1,000, and I used that Galambos-Enqueta residual stress pattern that I showed you earlier. And for 14145, I can't remember if I was at 0.3 sigma y or 0.5 sigma y, but nevertheless, we've got some residual stresses built in there. So some takeaways, some key observations, at least from the finite element world. The strength is reduced for initial imperfections and further reduced for residual stresses. As the slenderness gets long, all the curves approach Euler, but not precisely. They do come underneath Euler, and that was because, like we were talking earlier, of the bending, the deflections were getting very large. Partial yielding accentuated by residual stresses definitely impact minor axis strength more than major axis. And theoretically, we are going to end up with different strength curves from major and minor axis bending. Some additional thoughts is that these strength curves, we can't even define them major and minor for W shapes because they're also a function of the dimensions of the shape. Keep in mind I was showing you how the residual stress profiles change for light wide flange sections versus heavier ones. For other shapes, HSS, Cs, or built-up shapes, again, we're going to have very different compressive strength curves. So a gentleman by the name of Radar Behovda put together all of this data as part of his PhD thesis at Lehigh, in the late 60s and early 70s. And here's a plot out of Radar's thesis. And what we're looking at, again, is the ratio of the buckling stress to the yield. And on this axis, Radar used a different type of slenderness. That's what's across the bottom. But for A992, 50 over 29,000 square root is just a constant, and you would end up with the numbers that I'm showing in blue here. And the point is that what we're seeing here in this Milky Way are column curves for many different shapes and many different profiles, and major axes and minor axes. So it's a whole Milky Way, and AISC has decided to try to find one curve that goes sort of right down the middle. So that's where we're heading. So like I said,
Ron,
AISC,
can I interrupt you on
sure.
Residual stresses? We had a question on that. Doesn't the work that you do on a section, doesn't that add to the residual stress?
That's a great question. As it turns out, it doesn't actually add to it, but it often reduces it. I know that Bethlehem folks were looking at this years back, that the way you straighten a column after it comes out, they often use many different ways for straightening the column. And as a result of these different methods for straightening the columns, they took it right past yield and then relaxed it. And the second they did that, they sort of undid the residual stresses. So I've heard of that. Now there probably could be other cases, like I was saying, where you cold-form something else and you, on top of the residual stresses, may add some other ones. So it's definitely a complicated question that I don't think I could answer one size fits all. But there are cases where it definitely reduces the impact of the residual stresses. But I suppose we could also do some crazy things to it and increase the residual stresses, but they wouldn't be due to the thermal effect. They'd be due to the cold bending effect.
Right. Okay, and just one other thing. When you were talking about your test specimen and cutting it in sections,
yeah.
How can you slice a section without altering the residual stresses that you're trying to measure?
Yeah, that's a great question. I haven't done these tests before, but somehow when they cut them, it doesn't change it. But I totally agree with the person who's asking the question. You would think that would be the case, but it's used so often that it must not be changing it. But I don't have experience in doing it, but I do know it's a very, very popular method for doing it, and so must be very sharp saws.
Okay. Okay. Thank you.
All right. Now, like I said, we're going to now move to column curves for design. AISC has decided to use a single column curve to fit the experimental data and the analytical data, and this is for all column shapes. Okay. Other codes use multiple curves, and we'll take a look at that. Now, some background information, the AISC curve. First, Radar's thesis, if you can get a hold of a copy of it or the papers that he produced afterwards, it's a fine piece of work and definitely worth considering. The column curve that appears in our current steel specification is nearly identical to what Radar had, but it does have a small twist to it in the format of the equations. And Ray Tide has a nice paper on this in the Engineering Journal, which you can download at AISC, and if you're a member, it's for free. And he kind of gives you that background of how we got to where we're at today. So that one's worth looking at. And the history of all this stability and the background can also be found in this guide that Patrick was talking about that I had the pleasure of editing, the Guide to Stability Design Criteria for Metal Structures. So this is an 1,100-page textbook with sort of tons and tons of background on columns and beams and bracing or whatever you've got. But anyway, so I'd invite you to look at that. But let's move to what AISC did. So here's a picture again coming from a Radar's thesis I showed earlier. And the red curve going right down sort of the middle is the AISC column curve. So for a slenderness smaller than about 113, we have sort of a exponential, crazy-looking equation here that allows us to get this shape. And again, I think you'll find Ray Tide's paper showing you how we went from Radar's work and SSRC column curves to this equation. And once we get larger, than 113. Then things get a little bit more interesting. It's just 87% of the Euler buckling stress. So the 0.877 you've got to be thinking has something to do with the fact that there is the deflections are getting really large, and we decided to limit them. But so there's the AISC column curve, and I couldn't help myself but try to show you what happens when you compare it against those finite element results I ran earlier. The AISC curve is in red, and I've got the major axis curve, which would be above it. So AISC would be under-predicting the strength, so it might be conservative, but it is over-predicting the strength of the minor axis curve. But we've got phi factors and all kinds of other things going on, so no need to panic. It's just not possible for a single curve to capture all the different shapes. So I think it does a very good job, and so that's what we're seeing here. As I indicated, some other codes, let's take Eurocode, actually use multiple column curves. So if you were to design this member, you would go to their chapter E equivalent, and the first thing you would do is go to the lookup table and decide which one of the column curves on the left you're going to use. So, okay, I've got a wide flange section. All right, what is the ratio of the height to the width? Okay, is the thickness of the flange larger than smaller a certain value? And eventually is it major or minor axis buckling that I'm concerned with? And eventually I would find myself a column curve. And with that column curve, I would look up the value. And they have all the different curves depending on the cross sections. So you might recall again that we did have a difference between major and minor axis buckling and the strength of these curves. And it's interesting to see what happens in the Eurocode. So if I take that W14 by 145, its height to width ratio is less than 1.2, thickness of the flange less than 100 millimeters. For major axis buckling, I would use column curve B, and for minor axis, I would use column curve C. And you can see exactly what the finite element results were showing, and what we've learned through this lecture is that the minor axis strength is smaller than the major axis strength, and that's typically because of the havoc that these residual stresses are playing on. The combination of the yielding and the residual stresses are causing bending, and the bending stresses to reach yield earlier for minor axis than major. Well, we're almost done here. So the last thing in Euler was these support conditions. So I'd like to work through those and then put things in a summary for you. So on the support conditions, we've got a table that appears in the AISC, in the commentary to the AISC specification, but it's basically showing a whole bunch of columns, all right, just single columns, and all that's being varied is the support conditions on the top and bottom. So either deflection and rotation restrained, just deflection restrained, rotation restrained. Case D is the pin-pin column. Here's a cantilevered column, a reverse cantilevered column. So we've got all these cases, and the only one that we looked at and got all column curves for was the Euler buckling one. So let's try a different case. So the one we'll look at, let's say case B, where we have a roller at the top and a fixed base down at the bottom. So don't be confused. This symbol isn't so good by AISC. That point can move down. It just cannot move left or right. All right. I've changed up my coordinate system. I'm going to let the bottom be x equals 0 and the top equals x equals L, v of x to the left, and because the diagram showed the column buckling to the left. Anyway, I could set up my equilibrium equation just as I did earlier on. And what I would find out is that I'm required now to have some type of a moment down at this base because it is going to restrain the column. That fixity is going to restrain the column from bending down at the base, and we'll pick up a moment. So our differential equation, it looks just like the Euler equation from earlier slides, but we've got the moment term down at the fixed base on the right, so it no longer equals 0. So think of your old differential equations days. It's no longer a homogeneous differential equation, but a differential equation that's going to have a particular solution. So here's the solution, the Euler solution that we got earlier. All right, and again, go to your favorite differential equation solver and get it. And then here is what we call the particular solution. So we've got the whole thing. Let's throw on some boundary conditions. All right, so we put on our boundary conditions. We have 3 in this case. We know that down at the base there's no lateral movement. There's also no rotation down at the base. So the slope has got to be 0 in our deflected shape curve. And up at the top, there's no lateral deflection. So when we do that and use the approach that I showed you earlier for the Euler column, we would end up with an equation that would result in the elastic. Now I'm going to call this elastic as opposed to capital E, which is Euler. So the elastic buckling load being pi squared EI, then you'd find out that it's equal divided by 0.7 L squared. So we can reformat this into what looks like the Euler's equation, pi squared E divided by L over R squared, but we're going to introduce the K factor. And so in this case, our K factor would be 0.7. So we've got ourselves now an elastic buckling stress. If we go and have a look at the other equations here, the other conditions, the other support conditions, you can see that using those differential equations approach that we did for case B to get that 0.7, we could get the 0.5, the 1, the 2. So the next time you're on an airplane and you have nothing to do and you're bored, try to derive the K factors from your differential equations for the different support conditions. And that flight will be over before you know it, either because you fell asleep or because it was so interesting. Let's hope it was the latter. Anyway, now what I try to tell my students is that Euler really had something in that the Euler column, if you take a look at it, that was case D, had the pin-pin supports. And those pin supports are at locations where, at a pin support, the moment is 0. And we know where the moment is 0 is an inflection point. So if you take a look at the deflected buckled shape, let's say you sketch this one up, if you could just sort of locate the inflection point, that is where the curvature changed, the compression side changed from one side to the other, and call that an inflection point, found the other inflection point. If you could sketch it well enough, then just off your figure, you could almost estimate what the correct K factor is. And so you can see here the inflection point was at the top, and here about 70%. Not a good figure. I probably should have put the point down a little bit. No, maybe that's a little long. This one's sort of interesting. The inflection point is mid-height, but if we follow the column all the way down to its full Euler, it would actually, the K factor would be 1. K factor was 1 here. Our cantilevered column, follow it all the way down through the support, all the way to the second inflection point. The K factor is 2. Likewise, for this case, the K factor would be 2. So find the Euler column, measure the distance between the inflection points, and that's a quick way to get your K factor. But probably an exact way, of course, is to fire up your differential equations. The effective length is a function of the degree of column end restraint. All right, so these were very simple conditions, either rigid or pinned or some combination. But the degree of column end restraint in real structures, it can be very difficult to compute. So I'm showing you here a slide I stole off the web of the Walt Disney Concert Hall being put together. So it's a crazy-looking structure, and underneath that crazy-looking structure is a crazy-looking structural system. And if we just take one of the columns from there, I don't know, is that column pinned, fixed at the base? What is the lateral stiffness? What is the rotational stiffness at each end of the column? So if we could even, we have probably no idea what those values are, but if we could even get them, then we could go to our differential equations or our eigenvalue solver in finite element, and we could calculate ourselves a K factor. Now we could always go to the alignment charts, but not for this case. Alignment charts are great, but alignment charts come with a lot of assumptions. So if we start messing up on those assumptions, we're going to get into trouble. So all of this we're going to return to in Lecture 6, so stay tuned for that. So anyway, we've now undone Euler's last one, and that was the column end constraints not being pin-pin, and we did this through the use of a K factor. So our AISC column curve final take, we've gone through many different variations. All I've done here is just introduce the K factor. And so instead of it being the pi squared E over L over R squared, we've got the K factor in there, and everything else is there. So there's our AISC column curve. If we take a look at the Euler, we solved his equations, and then we undid all of the assumptions that were causing us trouble, and we got ourselves to a column curve. So in summary, what I did tonight for y'all, I tried to introduce the course and provide some of the fundamental stability concepts and definitions. Then we went on and looked at limit states of compression members, and I really focused heavily on flexural buckling. We moved all the way from Euler's 1744 solution, Euler buckling, all the way through to today's modern maximum compressive strength column curves. These column curves that we use in design account for the possibility of full yielding. They account for the possibility of bending due to initial imperfections out of straightness or the axial force not being quite through the centroid. They account for partial yielding, which is accentuated by the presence of residual stresses. So even if there were no residual stresses, the partial yielding could still bite us and reduce the strength of the column. And these column curves account for the degree of end restraint. Some other stuff that I did is I showed you the AISC column curve. Now Perry is going to focus more on that next week when we actually get into the design aspect and using that column curve. I also showed you at least what the Europeans are doing, but other countries also use multiple column curves. And then in a sort of a sneaky way, while I had the opportunity, I introduced you while we were there and working through these differential equations, how to get a moment amplification factor. I also showed you this stiffness reduction, a tau factor that appears in the direct stiffness method. Again, we'll be talking about that later, but had this golden opportunity where we were talking about residual stresses to introduce it. And I sort of hinted that for very simple systems, K-factors are easy to compute, and the more difficult the system, the more difficult the K-factor, more difficult the calculation for the K-factor. And eventually at some point, you just have to throw up your hand and say, I don't think I'm getting the right K-factor. And that's where this direct analysis method can really shine for you. So that's a summary of my presentation. Next week, like I said, Perry Green will be looking at the design of compression members. So he's basically going to pick up where I left off and hopefully provide you with a bunch of examples. And it looks like he's going to be looking at LRFD and ASD strengths for various shapes, and the possibility of flexural and flexural torsional buckling as well. So, Patrick, I think I'll turn it back over to you.
Thank you. Well, thank you, Ron. We have a couple questions here. First of all, the amplification factor that you were deriving, the 1 over, what was it, 1 over 1 minus P over P sub B?
Yep.
Is that the same amplification factor that we use in the AISC spec for the B2?
Well, first it's used for the B1 because it's only along the length of the member. Yeah, but it is the one in the AISC specification is modified to account for a variation in moment along the length of the member. So I'm going to hit that moment amplification factor again when I do session 5. So I'll be a little bit more clear on that. I was just trying to introduce the audience tonight to the concept with some pretty simple math. We can get to a moment amplification factor. But the one that actually appears in the specification, it's very similar based on the exact same concept, but it includes a C sub m factor, for example, for moment gradient and the like. So we'll be seeing that again.
Okay, great. And then on a finite element analysis, would you say that finite element analysis could be unconservative if you do not account for residual stresses? And then how would you account for them?
Okay. Yes, you need to account for, so what we're really talking about is the possibility of moving to what's now in Appendix 1, and that is you're going to try to use your own column curve that the finite element would provide you. And there, in Appendix 1, we say, yes, you need to account for those residual stresses in some way. So the answer is yes. There's a couple of different ways to do that. We've got a modified tangent modulus approach for frame analysis programs, and then all the way to if you actually build these things up, build up a wide flange shape using shell elements, you can also include within those shell elements, before you put any load on them, you actually can put in built-in stresses. So the studies I was showing you, that's how I did it. at the elements all along the flanges and through the depth. I used the Glambos and Ketter residual stress pattern. Depending where I was in the cross-section, I actually put in a compressive or tensile stress initially in those elements.
Okay. Okay, then the last question we'll get to today is if you have an axial load only and you don't know if the imperfection is on the strong or the weak axis, which equation would you use?
All right. There might be maybe I wasn't too clear right towards the end, but if there is the AISC column curve that we have in there, if you could go back a few slides there, Brent, to the one, let's say slide 77 for me.
Yep.
So down at the base, I'm showing you the AISC column curve. That curve includes the effect of the initial imperfection. So you do not need to be building the member initial imperfection into your model if you're going to be using the AISC column curve to calculate the strength.
Okay, that sounds good. Okay, thank you very much, Ron. Let me move on and close up our webinar for today. I do want to remind everybody about our CEUs. If you signed up for the individual webinar, that means that you paid the $185 for the connection, and you're going to be getting CEUs for everyone at your connection. Within 2 business days, you're going to receive an email from ceu@aisc.org, and that email will give you instructions how to obtain your CEUs. Follow the instructions on that email. It is an online form, and don't forget to check boxes next to each attendee's name, put each attendee in there, and then the CEUs will be sent to you. Again, this is going to be coming from ceu@aisc.org. And then for those of you who registered for the 8-session package, that is, our CEU is going to be 1 CEU for all 8 sessions, and that will be sent to you at the end of the 8 sessions. Now, I do have some more information regarding quizzes and recordings for the 8-session package. So those of you that just signed up for the individual sessions, you can sign off now. I want to thank you very much for attending. So for the 8-session registrants, there is going to be a quiz available. Access to the quiz will be emailed to you by this Wednesday, and it will contain a link to the quiz, and that email will be coming from nightschool@aisc.org. There are many reasons to take the quiz. If you would like a EEU, an equivalent educational unit, you must take all of the quizzes and the final exam to receive the EEU. If you watch one of the sessions in the recorded version, you must take the quiz to obtain your CEU or TDH. If you watch the live session, you do not need to take the quiz to receive your CEU. But if you watch recorded, you must take and pass the quiz to receive the CEU credit. Also, the third item here, the reinforcement. The quiz will really bring the knowledge that you learned today more clearly to you, and so we do recommend taking the quizzes. Then there will also be access to a recording for the 8-session registrants. Information for accessing this recording will also be sent to you by this Wednesday, June 5th, and that recording will be available for you until June 17th. And again, this is only for the 8th session registrants, and that email will come from nightschool@aisc.org. I just have a slide here on the schedules for us. We have the quiz and recording access you'll receive 2 days after the live session. The date that the quiz is due is the second Friday after the live session. The quiz scores will be posted 2 weeks after the live session. And you can retake the quizzes, and that due date is the third Friday after the live session. And then the final quiz scores and answers will be posted 3 weeks after the live session.